Hi everyone. So in this video, we're going to be talking about another method for evaluating improper integrals called the comparison theorem. So in order to introduce the comparison theorem, I first want to talk about a certain type of improper integral. So let's talk about improper integrals of the form the integral from a to infinity of 1 over x to the p dx. So what I want to talk about here is basically, depending on what that exponent is, does this integral converge or diverge? So there's a few that we already have seen, right? So we saw that in the previous video, we saw that the integral from 1 to infinity of 1 over x squared, we saw that that converges. Specifically, it was equal to 1. We also saw that the integral from 1 to infinity of 1 over just x, we saw that that diverges. So basically, there's some point at which it kind of switches from converging to diverging. And so that's what I want to try to kind of figure out right now. So I want to look at a couple more examples, and I actually put these on the on the worksheet that went with the previous video, but I think they're worth kind of going through together as well. So let's do the integral from 1 to infinity of 1 over x to the 3/2 dx. So how does evaluating this integral work? Well, again, we want to take the limit as as t approaches infinity. And we want to then do the integral of 1 to t of, and let's maybe rewrite this as x to the negative 3/2. So what's our antiderivative going to be? Well, we would add 1 to negative 3/2. And so that's going to give us, so we still have the limit. And then the antiderivative here, we would have x to the, so if we add 1 to negative 3/2, that's negative 1/2. And then we have to multiply that by the reciprocal of negative 1/2, which is negative 2. And we're evaluating this at t and at 1. So we get, if we plug in t, we get negative 2, or let me not forget about the limit part. So we have the limit as t approaches infinity of negative 2 t to the negative 1/2 minus, but then it will become a plus, right? Because we have a negative again. And then we have 2 times 1 to the negative 1/2, which is just 1. So we just have 2. Okay, so let's think about what this limit is. Well, let's maybe rewrite our the thing we're taking the limit of a little bit differently. So another way of writing this would be negative 2 over t to the 1/2. And then we have the plus 2. So one of the things we talked about in the previous video is that anytime you have something of the form 1 over t to any power, that limit is always going to be 0. And the same thing holds if you put a different number in the numerator. That doesn't make a difference. As long as you are taking the limit as t approaches positive or negative infinity of, t raised to any power, and that power is in the denominator, the limit is always going to be 0. So we would get 0 plus 2, which is 2. So it converges. So let's try one more. Let's try now the integral from 1 to infinity of 1 over, this time, x to the 2/3. So we just did 3/2, now we're doing 2/3. All right, so we got the limit as t approaches infinity of the integral from 1 to t of, and we can rewrite this as x to the negative 2/3. Okay, so in this case, our antiderivative, so we're going to add 1 to negative 2/3. So we're going to get the limit as t approaches infinity of, so x, if we add 1 to negative 2/3, we get 1/3. And then we take the reciprocal of that, and that's 3. And then we're evaluating this at t and at 1. So we end up with the limit as t approaches infinity of 3t to the 1/3 minus 3 times 1, which is just 3. So what does it mean to raise t to the 1/3? Well, that's like taking the cube root, right? And so what is the limit as t approaches infinity of the cube root of t? It's still infinity, right? Because it's not like over here, when we did this previous example, after we found the antiderivative, the t was in the denominator. So as t got bigger and bigger, the overall result went to 0, right? So when the t was in the denominator, the overall result went to 0. But this time, when we took the antiderivative, we ended up with a t that is in the numerator, right? It's not something over t to the 1/3, it's just t to the 1/3. And so as that gets bigger and bigger, it just gets bigger and bigger. And so the answer to this one would be infinity. And so this one, we would say it diverges. So what was it like? What's the difference between 3/2 and 2/3? They seem so similar. Why is it that this one ended up diverging, whereas the previous one converged? Well, notice that, like I just said, when we took the antiderivative with 3/2, we ended up with a negative here, right? After taking the antiderivative. So because our original thing was negative 3/2, when we added 1, we still had a negative, right? And so if we still have a negative power, that means that the t is going to end up in the denominator, and therefore the limit will be 0 of this part. And if the limit of this part is 0, well, then you'll just have 0 plus a number, because plugging in the other bound, you'll just get a number. Whereas here, because we started with negative 2/3, when we added 1, that brought us up to positive 1/3. And so we didn't have an x in the denominator, it was in the numerator instead. So basically the rule ends up being, and so this from here on out, you can just use this as a rule. You don't have to actually evaluate an integral if it's of this form. So if p, so remember p is representing here the exponent on x, right? Because we said at the beginning, integrals of the form 1 over x to the p. So if p is greater than 1, then the integral from a to p, or sorry, from a to infinity of 1 over x to the p dx converges. So it doesn't matter what that exponent is, as long as it's bigger than 1, you'll get something that converges. Because as long as that number is bigger than 1, when you take the antiderivative, you'll have something that's negative and then a number bigger than 1. So when you add 1, you'll get something that's still negative, like we did here. So even if it was, just to kind of give a quick example, even if you had something like the integral from 1 to infinity of 1 over x to the 1.01 dx, that converges. And so like I said, from here on out, you don't need to actually do that integral. You can just say it converges. On the other hand, if that exponent is less than or equal to 1, then the integral of 1 over x to the p dx diverges. And so why is that? Well, it's like we saw, if p is less than or equal to 1 to begin with, then when you have it as, you rewrite it as a negative exponent, when you add 1 to it, you end up with something that is positive. And so you're no longer having the situation you had in the previous one where the limit ended up being 0. So this is a pretty important fact, and especially in this video, we're going to be using this fact a lot. So just to give a quick example of this one, so if you had the integral from, let's say now 2 to infinity of 1 over x to the 0.999, that also diverges. And we also saw that 1 over x diverges, right? So even if that exponent is equal to 1, it still diverges. Okay, so we're going to see now how we're going to be making use of this. So let's think about an example. So let's say that we are trying to evaluate the integral from 1 to infinity of 1 over x cubed plus 1 dx. So you could evaluate this using partial fractions. There actually is a way to factor. I know it doesn't look like it factors, but x cubed plus 1 you actually can factor. And so you could use partial fractions and get to your answer that way. But there's actually an easier way to evaluate this. So we're going to kind of go to another page and then come back. But eventually what we're going to do is we're going to evaluate this integral by comparing it to an integral of the form the integral from 1, or I should just say a to be more general, a to infinity of 1 over x to the p dx. So this is basically, if you remember in Calculus 1, we learned something called the squeeze theorem. This isn't like the same as the squeeze theorem or anything, but I think the kind of, the method of thinking that it requires is a little bit similar to the squeeze theorem, because what we're doing is we're going to start with an integral that would be kind of annoying and in some cases maybe even impossible to evaluate. And what we're going to do is we're going to compare it to a simpler integral, to an integral that we do know how to evaluate it. And then we'll see that that comparison it won't let us figure out the exact value of the integral, but it will let us figure out whether it converges or diverges. So that's what we're going to be focusing on. And basically all the examples in this video, we're not going to actually find a number. We're just going to say either it converges or diverges. Okay, so this is what's called the comparison test or the comparison theorem. I think people call it both. Okay, so first step here is I'm going to say, suppose that f of x and g of x are continuous for x greater than or equal to a. And this isn't something we're really going to have to worry about. It's just kind of a technicality, but basically all the functions we've been working with have been continuous. Maybe they have an issue at a certain part, but they'll be continuous at the parts that we're actually focusing on. The other thing that needs to be true in order for you to use the comparison theorem is that they both have to be positive for at least a certain part of them. Okay, so that's kind of the technicalities out of the way. So let's say that you have a function f of x, and you know that that function converges. So I'm just going to sketch some random graph of what could be f of x. So let's say this is f of x, and let's say we know it converges. So let's say now you have another function g of x, and you don't know how to evaluate the integral of g of x, but somehow let's say that you know that g of x is actually less than or equal to f of x. So this blue graph is g of x. And I should also put in here, we're doing some kind of a improper integral. So let's say we're starting here at a. So what the comparison theorem says is that if the integral from a to infinity of f of x dx converges, and g of x is less than or equal to f of x for x greater than or equal to a, then we know that the integral from a to infinity of g of x dx also converges. So this is something I think I found that a lot of students, we'll see that there's a kind of another version of it that we'll do in a minute, and students kind of get them confused. And I think a lot of the confusion arises from trying to memorize this. And I just don't think this is something you really have to memorize, because I think if you just kind of draw a picture for yourself, it will sort of make sense, right? Like, what does it mean for an improper integral to converge? It means that the area, so if we were to take this integral of the black function of f of x, if we were to add up all the area extending on infinitely, if this integral here converges, that means that that is a finite number, right? It means all of that infinite area is some finite number. So now if we're saying that our other function g of x is always less than or equal to f of x, well then that area is going to be even smaller, right? Like there's no way that it could be bigger if the function itself is smaller. And so if the area under the top function is a finite number, well then the area under the bottom function also must be a finite number, just because of, comparing numbers, right? If one is bigger than the other, then the area has to be bigger than the other. So let's see how we can apply this to the example we just did. So what is a function that we know for sure whether it converges or diverges? Well, we know that if you have 1 over x cubed, we know that that is going to converge. So let's say, let's let f of x equal 1 over x cubed. Then the integral from 1 to infinity of 1 over x cubed dx converges. We don't care what actual value it has, but we know it converges because the exponent, 3, is greater than 1, right? And we just said on the other page that anytime that exponent in the denominator is bigger than 1, it converges. So what can we say if we were to compare our function here? So let's let g of x equal 1 over x cubed plus 1. So let's think about how g of x and f of x compare to each other. Well, think about how fractions work. What happens when you make the denominator of a fraction bigger? So what happens, for example, if you take, let's even try a number. Let's say we plug in 2 to both of them. So if you plug in 2 to the first one, you would get 1 over 8, right? If you plug 2 into this, you would get 1 over 2 cubed, which is 8. Sorry, which is 1 over 8, right? Because you get 8 in the denominator, so you'd get 1 over 8. What happens if you plug 2 into this one? Well, you would get 1 over 8 plus 1, or 1 over 9. And 1/9 is smaller than 1/8. So anytime you take the denominator of a fraction and make it bigger, that has the result of making the overall fraction smaller. So what does that mean? That means that our function g of x is less than or equal to our function f of x for all x greater than or equal to 1. And so what can we conclude from this? Well, by the comparison theorem, since the integral from 1 to infinity of 1 over x cubed dx converges, if this other function we're focusing on, because it's smaller, then that integral also has to converge because it's smaller. It's below the other one, and we'll look at a picture of that in a second. So let's look at the graphs of these just to kind of really convince you. But I think it's really valuable that you understand this idea of if you make the denominator of a fraction bigger, it makes the fraction smaller. That's really what's going to kind of come into play on a lot of these. So right here I have the graph of, let me just make this bolder. So this is the graph right now in black of 1 over x cubed, and we're focusing on this positive part. And then in blue, this is the graph of 1 over x cubed plus 1. So notice that it is below the graph in black. And so therefore, if the area from 1 onward under the black graph is a finite number, then the value of the area under the blue function should also be a finite number. Okay, so let's do another example. And then we'll also see that there's kind of the reverse of what we just found with the comparison theorem. So really, I should have said this on the last example. We're not finding the value. We're just determining whether an integral converges or diverges. So we're going to determine whether the integral from 1 to infinity of sine squared of x over x squared dx converges or diverges. So the first step with these problems is basically to figure out, what function are we comparing this with? So what would make sense to compare this with? So in this case, generally you're just looking for what's the power of x that you have in your denominator? So let's let f of x equal just 1 over x squared. So what can we say, and maybe let's also call g of x, let's let that be sine squared of x over x squared. So what's the comparison between f of x and g of x? Well, sine of x, if it wasn't squared, right, we know that sine of x is between -1 and 1, right? For any value of x, sine of x is always between -1 and 1. So what about sine of x squared? Well, sine of x squared, or maybe I'll say sine squared of x, that is less than or equal to 1, right? Because if you take a number, whether it's negative or positive, if you take a number that's between -1 and 1 and square it, you're going to get a result that is less than or equal to 1, right? If you take a fraction, if you take 1/2 and square it, it gets smaller, right? Or if you take 1 and square it or -1 and square it, they're 1. And so you're never going to get a result when you take sine of x and take that whole thing and square it. You're never going to get something that's bigger than 1. And it's also, I guess maybe we could even say this, this isn't super important, but it's also going to be positive because it's squared. But that's not really the important part here. The important part is that, so let's compare these two functions now. So we have one function that's 1 over x squared. We have another one where the numerator is always less than or equal to 1. So what happens when you take the numerator of a fraction and make it smaller? Well, the whole fraction gets smaller, right? So when you make the denominator bigger of a fraction, the fraction gets smaller. But also when you make the numerator smaller, the whole fraction gets smaller. And so because sine squared of x, it's going to be all sorts of different values, but those values are never going to exceed 1, and oftentimes they'll be less than 1. And so therefore we can say this means that g of x is less than or equal to f of x for all x greater than or equal to 1. And so now we can apply the comparison theorem. So by the comparison theorem, because the integral from 1 to infinity of 1 over x squared dx, we know that converges, right? And why does that converge? Because the exponent is bigger than 1. So that tells us that the integral from 1 to infinity of sine squared of x over x squared dx also converges. Okay, so there's another version of the comparison theorem, which is basically the other way around. So we're still going to use these same kind of things at the beginning. Maybe I'm going to make this a different color so that doesn't look like it's grouped with that. Okay, so we're still talking about functions that are continuous, and we're still talking about functions that are positive. But now let's say that you have a function that actually diverges. So again, I'm going to draw a function f of x. And let's say it's like 1 over x or something. So let's say it diverges. And then let's say that g of x now is a function that is greater than or equal to f of x. So if the first one diverges and the second one is even bigger, well, that should diverge as well, right? So basically what we're saying here is that if the integral from 1 to infinity of f of x dx diverges, and if the function g of x is greater than or equal to the function f of x for all x greater than or equal to a, then the integral from 1 to infinity of g of x dx also diverges. And I've found that students, for some reason, get these mixed up. And I just think if you took a moment to just draw a picture, it would make sense, right? Because it's just like areas. It's like if one function is taller, then its area is going to be bigger. So if the bottom function already has an infinite area, well, then of course the function above it is also going to have an infinite area. So let's see an example of how this one would work out. So let's say now we're trying to determine whether the integral from 1 to infinity of 1 plus 5 over x dx converges or diverges. So this one's a slightly funny example because really we could actually take this, we could rewrite this fraction a different way where we could split it up. But let's say we didn't want to do that. We wanted to just kind of look at it and figure out whether it converges or diverges. So what do we want to compare it to? Well, again, you just look at what's the exponent on the denominator and use that as kind of your base function to compare it to. So let's let f of x equal 1 over x. And let's let g of x be this function. So 1 plus 5 over x all over x. Well, then what happens if we compare these two? Well, if you take 1 and you add 5 over x to it, so 5 over x, if we're talking about positive numbers, which we are, right, because we're looking at we're taking the upper bound towards infinity, we're always looking at positive numbers. And so that means that 5 over x is always going to be a positive number. So maybe let me even write down kind of one more step. So 1 plus 5 over x is going to be greater than or equal to 1, right? For all x greater than or equal to 1. And so if the numerator is getting bigger, then that tells us that the whole fraction is bigger, right? So g of x has to be greater than or equal to f of x for all x is greater than or equal to 1. And so what does this tell us? Well, by the comparison theorem, because the integral from 1 to infinity of 1 over x dx, we know that that diverges. And so if our function is even bigger, then that integral also has to diverge, right? So the integral of 1 plus 5 over x dx, that must also diverge. So I want to look at one more example so we can see a situation where actually the comparison theorem does not work. So let's say that we're trying to evaluate the integral from 1 to infinity of 1 over x cubed minus 1 dx. Or sorry, we're not trying to evaluate it, we're just trying to figure out whether it converges or diverges. Okay, so let's try to use the comparison theorem and we'll see kind of how it falls apart. So if we wanted to use the comparison theorem, we would probably want to compare it to f of x is equal to 1 over x cubed, right? Because that's kind of the most similar simple function that we have. And then g of x would be equal to 1 over x cubed minus 1. So if we compare these two functions, let's think about which one is going to be bigger. So what happens if we take, and we can even try a number, and that goes for all of these. If you're confused about which one's bigger or smaller, literally just pick a number and plug it in. Just make sure that it's a number that's in between these bounds. So for example, if we plug in 2 again, if we plug in 2 to the first one, we would get 1/8. If we plug in 2 to the second one, we would get 1/7. And so which one's bigger, 1/8 or 1/7? Well, actually 1/7 is bigger. So what happens to a fraction when you take the denominator and make it smaller? The fraction actually gets bigger. So that would tell us that g of x is actually greater than or equal to f of x. So we'll see that this actually doesn't help us. So why does this not help us? Because, so what do we know? We know that this converges, right? 1 over x cubed, if you take the integral of that, it converges. And we just figured out that this function is bigger than it. That doesn't tell us anything. That doesn't tell us that it converges because, we would need to know the function was below to know that it converges. It also doesn't tell us that it diverges. It just doesn't really tell us anything. So let me kind of write that down here. So basically, because the integral from 1 to infinity of 1 over x cubed dx converges, the comparison theorem just doesn't tell us anything here. And this is one of those things I think it's maybe a little confusing. Like, I feel like I can try to say it in as many words as I can, and it might not quite click until you kind of sit down and think about it yourself. Draw a picture. So, like if we have one function that we know converges, so here's, let's say, f of x, so we know this one converges. And then we have another function that all we know about it is that it's above. If we know it's above, that doesn't tell us that it converges. It also doesn't tell us that it diverges because we don't know how much above it is, right? It could just be a tiny bit above and it could still converge. So basically, when you're trying to use the comparison test, you need to first figure out what are you trying to compare it to, and figure out which one's bigger, which one's smaller. And then once you figure out whether your known integral, meaning like this one, converges or diverges, that will tell you whether you'll actually be able to apply the comparison theorem or not. All right, so that's it for this video. In the next video, we will continue to talk about improper integrals, and we'll actually talk about a different type of improper integral where instead of one of the bounds being infinity, the issue will be that we'll have an infinite discontinuity within our bounds. So I'll see you in the next video.